Welcome to another podcast. In this episode, we're going to be taking a look at exponential models, and we're going to sort of split our attention between exponential models of growth and exponential models of decay. But more generally, we're going to be speaking about what are the basic elements of an exponential model. So most of us know that if we're talking about linear models, then we're looking at things of the form y equals mx plus b. And if we're thinking about sort of the way that this would look in sort of a table format here, when we talk about linear functions, then typically with linear functions, if you think about their x values and their corresponding y values, then we all know that when x is 0, you get the intercept b, and then when x is 1, you get m plus b. When x is 2, you get 2m plus b. When x is 3, you get 3m plus b, and so on. The point being here that each additional step adds m. So the slope is added for each additional step. Now let's contrast that. So this is a linear model. Let's contrast that with what an exponential model does. Exponential models are models of the form y equal a times b raised to the x power. So there's a power involved in the x variable. The independent variable is in the power. If we look at a similar sort of description for exponential functions, then you can see that on a sort of table basis here, when x is 0, y is a. When x is 1, y is a times b. When x is 2, y is a times b squared. And when x is 3, y is a times b cubed. So the value b is multiplied for each step. So the idea is you're increasing the size based on the previous size. Here, you're increasing the size based on a constant amount. That's the difference between linear and exponential. Exponential increases depend on the previous size of the value y, whereas linear functions only increase based on the value m, which has nothing to do with how big y is. So the point here is that the rate of change is proportional to the size of the dependent variable, which in this case is y. That is the major difference between linear and exponential models. Now, a couple of things that we can pick out immediately from this is because when x is 0, y is a is often called the initial value. It is the y-intercept of a exponential graph. The value b is called the common ratio. And the reason that b is called the common ratio is because if you look at the ratio of any two terms, for example, if I look at ab divided by a, that's the ratio of the first two terms. That ratio is b. If I then look at ab squared versus AB, that's the previous term, that ratio is B. The point is, to get from one step to the next, you're always multiplying by B. So the common ratio here is B. And depending on whether B is large or small in its relationship to 1, if it's bigger than 1, then these quantities are going to grow. And if it's less than 1, these quantities are going to shrink. So maybe just say a couple of words about that. When b is greater than 1, then b is a growth factor. When b is less than 1, and really what I mean is in between 0 and 1, then b is a decay factor. And if b is equal to 1, then there is no change occurring. It's neither growing nor decaying. So the b value is very dependent upon its relationship to 1. If you're multiplying by values larger than 1, then the dependent variable y is increasing. If you're multiplying by variables between 0 and 1, then you are decaying or getting smaller, and if b is equal to 1, then there's no change occurring. Now, one question that often comes up is how to solve for x. And so if you look at y equals a times b to the x, if I want to solve for x, then I'll start off by dividing both sides by a here. So y over a equals b over x. Then the next step would be to take the logarithm of both sides. So the logarithm of y over a is equal to the logarithm of b over x, and the reason you do that is because the logarithm is the inverse operation to a power like this, and we can use properties of logs, and one of the properties of logs says that when you have the logarithm of something raised to a power, you can bring the power outside the logarithm multiplied by it, and then it's just the logarithm of the base. So sometimes this b is called the base as well. So if you hear me talk about the base of an exponential, that's referring to the b value. And so finally, sort of the last step here is if I want to solve for x, if you look at that, x is equal to, I divide log b over, x is the log of y over a, divided by the log of b. So if you ever wanted to solve for x, this is the way to go about doing it, using logarithms. Now, what's interesting here are a couple of terms. One term is the term doubling time. So if you ever hear us talking about doubling time would be the amount of time it takes for the initial value a to double. So in this case, I would be looking at y being equal to 2a because it's doubled. And so if you take x, I'm going to call it x sub d, so it's the doubling time, then I would be looking at the log of replace y with 2a, so 2a over a, divided by the log of b, and if you do a little bit of algebra inside the log here, 2a divided by a is just 2. So you get the log of 2 divided by the log of the base. So this is the easy way to remember the doubling time formula. The 2 here represents double. It's the rate that you're looking for, and you simply just divide by the log of the base to figure out how long that's going to take. So this is the amount of time it would take for a quantity to double at a given growth rate of b. Similarly, you look at something called the decay rate or the half-life rate. And so if we look at the decay associated with the half-life of an object, that is talking about how long it takes for the object to be reduced by half. A common example of this would be radioactive isotopes. The amount of radiation they put off decreases exponentially over time, and so we oftentimes will look at the half-life, which is how long it takes for the radiation to be reduced by half. And so this would be x sub h, so the half-life there, and that would be the log of replace y, so I'm looking here, replace y with a over 2 this time. So I would have a over 2 divided by a over the log of b. And once again, if you simplify inside the log here, a over a would cancel, and that would leave me with a log of 1/2 divided by the log of b. And so the amount of time it takes for something to decrease by half when you are exposing it to exponential decay, you can see here that the half-life involves the number 1/2 inside the log because it's referring to halving. You could similarly come up with rules for tripling time. So if I wanted to talk about the time it takes to triple, you could see that a tripling time would be the log of 3 divided by the log of b. But that is the basic sort of formula here to control how to find the x value. And you can do that by hand or you can do it in the calculator. We're going to talk about ways to handle this in the calculator throughout the next couple of weeks. Depending on what class you're in, what calculators you're using, this is going to look different, but you can always revert to doing it by hand as we've seen here. So the main takeaways from this video are: do you recognize an exponential model when you see one? Do you know what an initial value of an exponential model is? Can you tell me what its common ratio is? Do you understand how exponential growth is different than linear growth? Are you able to solve for the x variable using logarithms? Do you know what the doubling time and decay and half-life time are for a given exponential model? These are the kinds of things that we're going to be interested in. But probably the most important thing to take away are these values of b. So understanding for different values of the common ratio b what the model is doing. All right, in future videos we're going to take a look at this specifically applied to finance, and so make sure you take a look at those, especially the compound interest problems, as that's going to be a major component of this unit. All right, thank you for watching.